Section 2.2 is all about equivalence relations and the corresponding ideas of equivalence classes and partitions. We saw an example at the end of the previous video where a relation turned out to have three nice properties. We said those are the properties that equals sign has, and that is the definition of an equivalence relation. So an equivalence relation is trying to capture the idea that two objects in your set are the same. The definition is that the relation R on S is an equivalence relation if it's reflexive, symmetric, and transitive. So those are the three things that we need to check if we want to see whether we've got an equivalence relation. Like in the previous video, we saw that we did have those three things. So congruence modulo n is an example of an equivalence relation. Also, equal sign is an example of an equivalence relation. There's often some special notation for these. So we might write this symbol, which is sort of tilde symbol, like this, if it's an equivalence relation we're talking about. Instead of writing A, R, B, we might pronounce this A is congruent to B, or we might say that A and B are equivalent. I can say it like that because the equivalence relation is symmetric. We know that if A is related to B, then B is related to A. So we can use the shorthand A and B are related, or equivalent, or congruent. There are other symbols that we might use. This triple equals sign is popular, with three lines in between. You might have met that before, and you might have met it for one of these examples that we've got. I've got three. So if your set is the complex numbers, then there's an equivalence relation defined by complex numbers with the same modulus. So first, that sets up a relation. It says that Z and W are related if they have the same modulus. And then that turns out to be an equivalence relation. And really it's inheriting that from the fact that equals is an equivalence relation on the reals. If you go and check the three properties for this, reflexive, symmetric, and transitive, then you'll find that really you're checking them for the reals after you've taken the modular sign of three random complex numbers. But that's an equivalence relation on the complex numbers. They're the same distance from the origin, if you like. If S is polygons in R2, then we have an equivalence relation defined by congruence. You might have met this for congruent triangles. They have the same shape and size, but they might be mirror images of each other. That's an equivalence relation all the same. Any triangle is congruent to itself. If you have a pair of triangles, then they might be congruent to each other, in which case if X is congruent to Y, we said Y is congruent to X, that's the symmetry. And then also transitivity. If you have three triangles, that pair's congruent, this pair's congruent, then the first of that are also considered congruent. You might have met that one before, possibly with triple equals equivalent sign. And an example using functions, which you might have met before, they're in chapter 3. If we're looking at differentiable functions, then we have an equivalence relation if they have the same derivative, if we consider them to be related when they have the same derivative. And you know that doesn't mean that they're the same function. You never forget the plus c when you're integrating, I'm sure. One more example, it's the congruence again, because I want to show you this notation that people use for congruence modulo n. Instead of writing A, R, B, or even A congruent to B like this, people sometimes write something a bit more like this, A congruent to B modulo n, where the congruent sign is the triple equals sign, and modulo n appears in brackets like a kind of terms and conditions on the end, with modulo abbreviated to mod. So you might say A is equal to B mod n. That notation kind of sets up the relation to say that A and B are related and reminds you that it's an equivalence relation, that these things are in some sense the same integers that differ by a multiple of n. Okay, let's look at the notion of an equivalence class now. So if you've got an equivalence relation, then we can set up an equivalence class. We say the equivalence class of X is the subset of elements in S that are related to X. And that set is sometimes denoted x bar like this, or sometimes x in square brackets. And it's a set. It's all the things that are related to x. So it's not the same thing as x itself. Even though, of course, because of reflexivity, x is in that set. X is related to x, so x is in there. But it's a set of things, maybe just x, but maybe other things as well. And remember, we're not getting confused between an element and a set containing that element. Anyway, in this example, for congruence modulo n, the equivalence class of 1 is the set of things that are equivalent to 1, which is things that differ from 1 by a multiple of n. So we have 1 plus n, 1 plus 2n, 1 plus 3n, or 1 minus n, 1 minus 2n, and so on in both directions. So that's a set. I want you to notice really that 1 and the equivalence class of 1 are different things, although sometimes people do stop writing the bars on the top or square brackets or whatever if the context is clear, or if they're using some notation like that modular arithmetic notation that we saw before. People really might stop writing those, but we should write bar on the top to indicate the entire equivalence class. The temptation, of course, is that, well, all those things in the set are equivalent. I'm considering them all to be equivalent to each other, so if I squint, there's only really one thing in there, and then I'm feeling lazy, so I set with one thing in, I might just write the thing, but we've got to do better than that, haven't we? Right, okay. 1 bar is not the same as 1. The first is an element, and the second is a set of elements of S, including 1. Okay. We can talk about the set of all of these. So this is called a quotient set, or the quotient set for a given equivalence relation. I'll come to the notation in a second, but the idea is that you take equivalence classes of every element in S. So explicitly spelt out down here, it's a set of sets. Inside this one, it's all y in the set that are related to x, where x is just something in S. So x ranges over everything in the set, and you get lots of different equivalence classes. Or maybe you don't, because of course inside this outer set, inside this set, remember that things that are the same don't have any special meaning in a set. So there might be lots of copies. And in fact, there probably will be. That's sort of the whole point. There are lots of different ways to write the same equivalence class if there are lots of things in that equivalence class, because they're equivalent. Thinking about modular arithmetic, let's say modulo 5 to fix a number. I could write 1 bar for the equivalence class of 1, but I could also write 6 bar if I'm talking about modulo 5. Those are the same set. So although this looks like it contains lots and lots of sets, it really might not contain that many sets. For example, if I'm just talking about, if I'm just talking about odd numbers and even numbers along the top here, then I only have 2 sets in there. It's possible for your set to be infinite, but your quotient set to be finite. That's what's going on with modular arithmetic. Okay, so the notation for this is S and then a sort of division slash, and then the symbol for your equivalence relation. And that's supposed to evoke some sort of division, that you have a big set S and you have separated it out into things that are equivalent. So that, okay, we're not getting confused between elements and sets, but in this sort of big world, we've grouped together all the things that are equivalent to each other. And if we're just working with those, then we've divided by their sizes. Of course, not really division. We might be talking about infinite sets here, in which case there's no such thing. And the equivalence classes might not be the same size as each other anyway. But that's the idea, that we're taking our big set S and we're dividing it up into these separate parts. it is a set of sets, which I know that people find confusing. Back in one of the earlier videos, I tried to confuse you about sets that contained two elements, even though one of those elements might be a set itself. So I need to make sure we don't get confused by this. This is a set of sets. The sets are not so bad inside, just equivalence classes, things that are related to the element x. Okay, if in doubt, think about even numbers and odd numbers. Those are equivalence classes, and I can make a set containing even numbers, comma, all of the odd numbers, safely packaged up into two sets to make a big set which only has two elements, evens and odds. Okay. The advantage of thinking like this is we're trying to move to a point where we're ignoring the differences between elements. We've got an equivalence relation which says that they're more or less the same. So we don't want to mess around with the differences between m plus 1 and 2m plus 1. We want to just think about all of those as being the same. No, we can't, because they're not actually the same element, but we can bundle them up into these sets and then talk about the sets. And while you're talking about sets plural, it makes sense to package those into a bigger set. We're particularly interested in properties that translate from the elements to the sets, but that's a story for another day, I think. For now, let's define a partition, this idea that I've been waving in the air. The definition looks scary, but it's trying to communicate something quite straightforward about splitting up a set. So let's have a set on the screen. I'm going to draw some points for elements, and the idea of the partition is that we separate these out into different parts. We have some wider set, indicated by curly brackets, I suppose, and we've found a way to split up the elements. Here are the rules. So it's a collection of subsets of S with some rules. They're not allowed to be the empty set. That's not the case in my picture, good. They're not allowed to be the empty set. The union has to be the whole set. You have to get everything in your partition. You can't miss anything out. Every member of S lies in one of the subsets. And the intersection between two different subsets in your collection should be empty. They should be disjoint, nothing in both. So that, if you like, each element of S belongs to one and only one member of your collection of subsets. The subsets are called the parts of the partition, and in my picture at the top there are 4 of them, but I'm being pretty vague about how many there might be in general. There might be lots. I'm using an indexing set I for my subscripts, where there could be really a lot of these to split up all your elements into separate parts, and that's okay with me, provided that they do these 3 things. None of them are empty. You get all of the elements into one of your many subsets, or however many you've got, I suppose, and also that however many you want, you never put any elements into 2 of them. For I not equal to j, ai is disjoint with aj. Okay, so this is a very precise way of setting up this idea about splitting elements of the set into separate parts. And the reason I've brought it up is that an equivalence relation gives you equivalence classes which form a partition on your set. That's going to be proved in the course Groups and Group Actions later on in prelims, if you're taking that course. But it's not actually that hard to check. You might like to go through the definition of a partition and check whether the equivalence classes do that or not. In fact, let's do that together now. So looking at the definition, we need to check that for our equivalence classes, that none of them are empty. And that's just a matter of saying, well, the equivalence class x bar, for example, contains x. So that's all right then. It's not empty, it contains x. If it didn't contain any elements, I wouldn't be talking about it. I wouldn't have a name for it. Anyway, and then the second case is also easy. We need to make sure that every member of S lies in one of these subsets, and this is going to be a case of saying that X is in, this looks exactly the same as the previous statement, doesn't it? X is in X bar, by which I mean for all X in the set, X is in X bar. So that's the one to look in. And then the last one is a little bit harder. We need to consider the case that something could be in both AI and AJ, which for me are equivalence classes. So if Y is in X bar, that equivalence class, and also Y is in Z bar, so I'm considering maybe an element could be in two different equivalence classes, and I'm looking for a contradiction because I don't want that to happen. So what would that mean? That would mean that Y is related to X and Y is related to Z. So because of symmetry, X would be related to Y, and then I've got X related to Y and Y related to Z. So by transitivity, X will be related to Z. So in fact, these were the same equivalence class all along, if they have an element in common. So contradiction, it wasn't the case that I is not equal to J, those were the same equivalence class all along. So that's the sort of ideas of the proof for why an equivalence relation gives you equivalence classes that form a partition. Going the other way, maybe you can see that if you've got one of these partitions where every element of the set is split into parts, then you could define an equivalence relation just by saying that things in the same part are related to each other. That's definitely a relation. I'm saying it's pairs of elements that are in the same AI for some I. And maybe you can check for yourself, it's not that hard to think about, I suppose, that is an equivalence relation because it's reflexive, symmetric, and transitive. The concept of being in the same part is all of those things, which means that if you have a partition, you get an equivalence relation. And since this is an Oxford lecture, we have an Oxford example of such a partition. The students at Oxford are partitioned into colleges. The partitioning subsets are the sets of students at each college. Now, with some caveats, that really is a partition. We can check all three properties. Firstly, there are no colleges that are empty in terms of students. I'm ignoring All Souls College because I don't think it's got any undergraduate students, but maybe I don't have to. Maybe I can include All Souls. They have some people who are students, I think. Maybe. In part 2, every student is a member of a college. I think that's true. And part 3, I need to check the disjoint thing. So my counterexample would be a student at 2 colleges, but I don't think that happens very much at all. So that really is a partition with some caveats that every student is at exactly 1 college and there are no empty colleges. And then the equivalence relation induced by this partition, which is a good phrase, induced by this partition. That says that X is related to Y, equivalent, if and only if X and Y are at the same college, which is an example of how things can be equivalent without actually being the same, that you are very different from the set of people at your college. You're in that set, but you're not the same thing as that set. When I say your college students, that includes you. It's an equivalence class. It's you and all the other people at the same college as you. But that's a set. It's not the same thing as you at all. We can even think about the set of all of those sets, which is, well, I would say everyone together, but it's all of the sets together, right? It's the list of college enrolments in separate curly braces for sets. Anyway, that's a partition given by the structure of the University of Oxford. And that's all that I wanted to tell you about equivalence relations and equivalence classes. That's the end of section 2.